Thank you very much. And just check you can still hear me.
Sounds good to me.
Great. Okay. Thank you. And thank you for the invitation to join you for the webinar today. Yeah, I'm going to talk about large language models for health, um, and particularly around evidence synthesis and systematic reviewing. And I'm not going to necessarily give you the answers for every single question you might have in terms of can we trust what they say, but I think part of what I want to do is to encourage us all to critique tools and applications which are coming out all the time, and to give us some of the sort of like a critical perspective in order to say, well, actually, this could be useful in this situation, but actually for this situation, it probably isn't. So to some extent, sort of to open the black box and to have a little look inside in terms of how they work. So just a quick slide on where I am, and this is the building where I've been working for a long time, as it says here, part of UCL at the epicenter, where I've been working on systematic reviews, particularly interested in complexity and intervention complexity and questions around and beyond effectiveness. So interested in statistics, but also interested in qualitative evidence synthesis. And a long-standing area of work has been around automation and making the review process more efficient, very much as a means to an end, in that I'm interested in informing decisions using research, and it just takes so long to find the research and synthesize the research that for a long time I've been thinking there has to be a better and quicker way of this. We're slowly starting to see situations in which systematic reviews, or at least parts of them, can be automated, but there's still a long way to go. So what I was going to talk about is automation and systematic reviews. The story so far, and I think I've got one slide on that, just to sort of orientate us, and then start to think about newer technologies. And there are some enablers, I think, which are sort of facilitating their development and take up now. And then thinking about these large language models, this generative aspect of machine learning now, which I'm sure we've all experimented with. How can they be used in reviews is how I'm really thinking. When can they be trusted? And there's a lot of hype around them. Are they a game changer or not? So just to orientate ourselves a little bit, automation and systematic reviews, what can be done? And up until this year, very much this sort of slide sort of captured the area, really. We've got the review process on the left, from the study identification, mapping research activity, data extraction and synthesis, etc. And there was much more evidence that systems to automate systematic review processes were more effective towards the top of the list there. So for finding studies and for classifying studies, and to some extent mapping studies, we had more evidence of effectiveness, more situations in which we could use tools there. And that was, of course, partly due to the fact that there's just more data available for research and development in that part of the systematic review process. And to some degree, it has been easier for automation to solve those problems. So it's been easier to classify text as being relevant or not relevant, about randomized trials or not randomized trials, than it has been to say, do a risk of bias assessment, extract statistical outcome data, or actually synthesize the findings of these studies. So there's far more work thus far at the beginning of the process. And that's led to the development of what I've called traditional tools, which in some respects is slightly ironic in that the take-up of traditional tools is not universal by any means yet. But there are lots of tools now that enable you, when you're doing a systematic review, to rank and re-rank records, for example, when you're screening titles and abstracts. There are tools that will automatically cluster records for you to enable us to get a sort of like a sense, an overview of the distribution of research in a particular area. And classification, randomized trial classifier was one that is used more extensively than others because we've got lots of data that was available to train from. It's when we've been able to build a good classifier which says this is a randomized trial versus this isn't. And to some degree, we feel like we know where we are with these kinds of tools. And it's fair, I think, to say that they've been useful in various aspects of review processes, but so far they've not been game-changing in that reviews look much the same as they have for a long time. The demands placed on reviewers are higher now, in terms of workload and the amount of research that we have to look at, which means really that the time it's taking to do systematic reviews hasn't massively changed thanks to these automation tools. They're certainly making life easier, but they haven't been game-changing. So in terms of thinking about what's been happening over the last few years, there are some key enablers, I think, that have enabled the creation and the use of new digital evidence synthesis tools. So to begin with, there's increased availability of open access research. The Microsoft academic data set, I think, was part of a sort of fomenting this sort of like this cultural shift to having more open bibliographic data. All bibliographic data is not yet open yet, but bibliographic data together with citation availability is increasingly open. And what that's meant is that tools such as OpenAlex and Semantic Scholar are coming in, where essentially the vast majority of newly published research is available in those data sets. So there's 250 million records, for example, in OpenAlex now. So what we've been seeing is tools which have been able to be sort of piggyback on top of these data sets, which are increasingly comprehensive, containing the published, certainly the journal literature of REL's research. Allied to that, we've had increased computing power, both in terms of the amount of memory that a computer might have, and also just the raw processing power. And what that's meant is that we can process larger and larger data sets. And allied to that is that there have been advances in machine learning technology and machine learning algorithms. And they've gone hand in hand with this increased computing power. And so there are particular advances in machine learning technologies which have taken advantage of this increased compute and essentially parallelized processes. So rather than sort of starting at the beginning and working its way through and finishing building a model at the end, it's possible to parallelize a lot of this so that larger and larger data sets are able to be used in order to build machine learning models. So it's not necessarily a massive advance in terms of our understanding of algorithms, though there has been that, but actually just the ability of us now to be able to take advantage of cloud computing possibilities and the increased numbers of nodes you can have, for example, in a cluster, in order just to deal with larger and larger data sets. So what that's led to is this new generation of tools, and they're quite unsettling. They've promised to do more than just achieve minor increases. They seem to understand language, they can answer questions, they seem to be able to synthesize knowledge. And the possibility here is that they're going to change the review process more fundamentally than some of these more traditional tools. So the question obviously is, can we trust them? Can we use them? And I think a key aspect of why they're so interesting for us is actually sort of some of the theory that goes around reading documents for inclusion in reviews. Obviously, when we read something in the light of our existing knowledge. So when I read an abstract of a trial, for example, I'm reading it with my background knowledge of what a trial is, what it's for, how they're structured, challenges in recruitment, how you randomize, why you randomized. All of that theoretical knowledge is part of my understanding and my interpretation of when I read an abstract. And those previous examples that I was talking about, the RCT classifier, for example, doesn't bring any background knowledge to that task at all. All the classifier has in front of it is the text in the title and abstract, and that's what the model's built on, and that's what is used when we're predicting whether or not a given unseen abstract is an RCT or not. So there's been work over a number of years now, this hasn't just come about in the last couple of years, around making machine learning increasingly context aware. And so you've probably come across this concept word embeddings, and you might have heard even word tvec, and then you've probably heard the word transformer model, where what the machine learning community has been increasingly able to do is to develop models which do not simply have to deal with just the text that you might provide for classification, but actually there's a whole load more information, for example, about randomized trials, which can be drawn on in the statistical model. What's really important, though, still to bear in mind is that they're very, very large and sophisticated statistical representation of words and phrases that are co-occurring. And they are just statistical models. They are huge, and sometimes it's really hard to get your head around just how big they are, but they are statistical representations of the text that they've been trained upon. So when thinking about using tools which are using these new models, I think it's important that we still are grounded in terms of some of the core principles that we bring to systematic reviews and evidence synthesis. So the decisions that affect people's lives should be informed by reliable research. We know that individual research studies are atypical. We need to draw on the sum of current knowledge. So we use evidence synthesis. Evidence syntheses can be unreliable if we don't do them well, if we do them badly, or if the research that they contain is unreliable. And so those core principles can also be applied when we're thinking about using new tools for evidence synthesis. So these question answering systems that you might have seen, do they enable me to draw on the sum of current knowledge, or do they present me with an incomplete or a biased picture of it? Second key point is, does this question answering system, if that's what I'm using, or does it enable me to critique the research? Does it enable me to say, this I trust, this I don't trust, this is reliable, this is unreliable? Or what some of them do is just treat all text as equally reliable, equally valid. So one example of a sort of like a hybrid between the traditional use and the use of language models is what we've been doing in Epi Reviewer recently, where we've been taking advantage of one of the key enablers here, OpenAlex. We get updates of papers every month from OpenAlex. Up to about 800,000 new papers arrive every month. And we've got a number of reviews in the system. We build machine learning models to learn the scope of each of those reviews, and then the new papers are automatically added to the reviews. So the key enablers there are the fact that we've got lots of open access data, the fact that we can parallelize this work in the middle here, because scoring 800,000 papers against up to about 80 reviews, I think, are being sort of subscribed to the service at the moment. That's an awful lot of work. And so we parallelize those tasks in the cloud in order to cope with the scale of that. And what it's meant is that, for example, our map of COVID-19 research, we had a very manual process to begin with, and it's now fully automated. And we find actually that using the open access, OpenAlex source, for example, can actually lead to actually higher recall than using traditional sources. So from our point of view, we've done some validation work to be confident that it is valid in terms of drawing on the sum of the current knowledge that we expect to find in that system. And it does enable me or other users to distinguish between reliable and unreliable research, in that it's simply finding the research for people. It's not doing any kind of quality assessment. So it's trustworthy because actually it's not too far from traditional methods. The data set has been validated, and it uses machine learning, but you'd think in relatively standard ways. It doesn't actually output text and summaries. We use a language model, a transformer language model, but we don't actually get it to generate text. We use the statistical representation of language that it's got within a standard machine learning model. And that's fine for us, but we had a lot of manual training data. But probably quite key also is that we have a team of software developers and data scientists, etc., who were able to work alongside the evidence synthesis team to partially bespoke build a workflow for that. So there are lots and lots of possibilities here, but not everybody's got a software development team working alongside them. So we've got to think about, well, what do we do with some of these more generic and less tailored tools? And here, I think it's quite important that we start understanding what the language model actually is. Just got a quick question here. Do you search other search sources like Embase or Scopus? We did. For that workflow, we don't anymore. We just use the OpenAlex because it's got basically all of the newly published research, as well as the sort of like the preprints and that kind of thing. Where it's less full in terms of its comprehensiveness is clinical trials registry data, abstracts and theses, theses and dissertations, and abstracts from conferences, which you have to go to Embase to find. So large language models, they're statistical representation of text. So I've tried to summarize in sort of two-dimensional space here what it might look like. So think of this as a graph. We've got the y-axis, we've got the x-axis here, and we've got the word king, which is represented in this space here. King is sort of on the same axis as queen, obviously isn't exactly the same concept. And also then king will tend to be associated with the concept man, queen with the concept woman. So, but those are also concepts which are on a different axis. So I've kind of put that into the z-axis there going into the screen. Prince, the word prince in this sort of simplified space goes fairly close to king and man, but that's how sort of like older models used to do it. There's this number 2. What's going on there? We got prince, we got a number 2 at the bottom there. Newer models will say, well, actually, prince and the number 2 would go together over here because that's to do with project management and stuff. And there's another type of prince, of course, who is this musician. So we've got another part of the sort of like the jigsaw puzzle of words within our picture here, where the word prince might go with king, might go with 2 and to do with Gantt charts, and it might go over here to do with other singers, for example, Madonna. And of course, then prince would be closer to man, Madonna closer to woman, etc. And older language models didn't used to be able to make these fine-grained distinctions about the context. Prince would have been sort of represented as prince, and some of that contextually really important information would have been missing. So that's one of the jumps forward that we've had in the last few years, the ability to actually encode text in a way which has got more contextually aware data around it. So the concepts here in our graph can be represented statistically, if you're used to coordinates on a graph, king and queen, and you can calculate the distance between them. Obviously, I'm simplifying things quite a lot here, but what I'm trying to get across is that whilst this is a simplification, this is basically how a language model represents words and correlated words. So the number of dimensions is far larger. I had 3 there. The OpenAI language models for ChatGPT, for example, have got about 1,500 or so. So it's an impossible space to sort of visualize in 2-dimensional form. What's important is that there's iteration in the development of a language model where the model is repeatedly prompted to predict an extra or missing token. I won't go into what tokens and words are. We can think of them basically as more or less interchangeable. And you can see in this example here, the quick brown fox jumping over the lazy dog. What the machine learning process might do is sort of mask out the word fox and lazy. And then when the machine learning guesses, if you like, predicts the right word, it gets rewarded for that. And it's iterative and it goes round and round until it gets really good at predicting missing or the next words. There's more to it. As you might expect, there's something called reinforcement learning from human feedback, where in addition to building a language model, there's then this work which is done in terms of giving prompts to the language model and then scoring its results in terms of whether or not they were appropriate or not. And so there's been, and this is where the scale of this work starts to become difficult to sort of understand, in that there are probably millions and millions of questions and answers that have been scored and rated and then used to improve the model. And that's one of the big advances of the OpenAI chatbot and the others that you've seen, in that they're able to identify what a question is asking them and actually then also give an appropriate response. It's not always right response, but actually the context of the question appears to be understood, if you like, by the model, and an appropriate response generated. And that's partially due to this big piece of work around the model, which is around reinforcement learning. So just to give you an example, all of these numbers here, I extracted an intervention term from one of the systematic reviews we were looking at, which was standard booklet or culturally specific booklet. So that's part of an intervention. And those numbers in the background are all is the sort of like the statistical representation in that graph space of that concept. And so you can see the number of numbers vastly exceeds the number of letters even in the words there. And that's due to the fact that it's trying to represent that really quite precisely in terms of the distance of those concepts from everything else in the vector space. The last little bit of tech, I promise we're going to move on from this in a sec, is just so that you are orientated in terms of encoder, decoder. You might have heard mentioned in different situations, and they're not really totally rocket science. The encoding of text is around that transformation of text, for example, where we've got here, standard booklet or culturally specific booklet in an intervention into that numeric form. So that's the encoding representation of that text. And then decoding is what you see at the end coming out of ChatGPT, where basically you've taken the numeric representation and turned it back into text, where it might be using to be sort of generating the next most likely word that you see in ChatGPT. What's interesting here, and that's why I wanted to sort of just take you through a little bit about the tech of it, is that you can do interesting things combining these different parts of the system. So for example, here I've got some abstracts, titles and abstracts about smoking cessation. And what I did was I asked actually ChatGPT, using the API, to extract from the abstract the intervention. So I submitted abstracts to it and I said, give me the interventions. And so it's actually quite good at being able to look at an abstract and extract information. That's one of the purposes that you can use these models for. So once I had that intervention, I then used another language model and transformed it using the encoding into numeric form. And what that gave me was a precise, relatively precise position of this intervention in the space of that language model. And the reason that's interesting is that you can then start to look at the similarity and dissimilarity of text in a much more context sensitive way. So you can then sort of visualize where this is a large amount of number of studies on AI and sort of equity and trust in AI. And what I've found doing this is you get far better clustering, you get far better positioning of the titles and abstracts in this case in relation to each other than you do if you're just relying on what those words in the titles and abstracts are alone. It makes sense because you're getting far more contextually rich information which informs which abstracts are likely to be closer to one another. But actually, when you start using it like that, you realize actually that there is quite a lot of value in terms of using the language model to understand the relatedness between research papers. And that's obviously quite an important concept for us in systematic reviews, because when we're trying to find studies for inclusion in reviews, or we're trying to update reviews and find the new studies that have come out, actually knowing quite precisely whether paper A is close or related to paper B is really quite useful. Okay, so that was it in terms of the sort of like the most, I don't know, the most technical input in terms of this. I'm going to start talking about tools now, but hopefully that sort of helps us to think about a little bit about how those models work. And then when we see a new tool, something around, well, okay, so what's actually going on under the hood here? So there are lots of these new tools emerging. ChatGPT is obviously one, there's the famous one. Connected papers, Cite, Elicit, Claude 2. There's many, many more. I'm not going to cover all of them here. The key challenge for us is everyone is using them. So can we trust them? How can we know if we can trust them? Are they going to change the game? So it's really important to understand how the tool has been put together, what its architecture is. So there's many sort of question answering systems coming out, for example. ChatGPT is obviously the famous one here. And the thing is that we can actually critique the validity of these tools using sort of like our standard, almost sort of what we learned in terms of research methods right at the very beginning. So for a start, we can critique ChatGPT very easily by asking the question, actually, does it contain the training data, or does the training data that it was trained on contain the answers I need? If we remember sort of thinking back to those principles about wanting to draw on the sum of current knowledge. Because we know, for example, that its training data ended on sometime in September 2021. And so if the answers we're interested in, or if we're interested in things that are up to date and things happen since then we know that the trained data just aren't in, the ChatGPT doesn't know about it. That's number one. Number two is that we're interested in research evidence, and a lot of the research evidence we're interested in, sadly, is behind paywalls. And so we know that it's not in that sort of open web space which a lot of these tools are being trained on. And so if the answers, again, we're interested in, we don't always know, maybe it sort of buried within paywall documents, again, those answers cannot be within ChatGPT. So what can be in there, and what we will often find there, is situations where the information has been freely available on the web in multiple places, and the language model is able to sort of memorize the treatments, the interventions, etc., and the answers to questions about them. So if it's seen it lots, it's out there online, the language model might well get that one right. And we know that these language models do get things right fairly frequently. But if you ask it a question about information which may be in a paywall document or something on which there is uncertainty, then maybe actually you will not get the right answer. The other situation is in terms of this hallucination thing. Does it make up answers? Yeah, because it's, the idea is behind the model is it predicts the next most likely word, or depending on how much sort of creativity you're offering into it, it might predict sort of some fairly likely, but not the most likely next words. And there, of course, by design, the system isn't actually designed to be correct. It's designed to be plausible. And we've seen the text. These language models come up with very plausible text. But by design, it's actually not checking whether or not the words and the phrases are actually factually correct. That's not how they're designed. That's not what it's designed for. The other type of architecture that these tools are increasingly using is a language model plus an external source of data. And again, we can critique those systems. We don't have to treat them as black boxes. What's the data set? What is in the data set? Does it contain the answers I need? Does it contain the studies that I would expect to find if I was doing the search myself? Does it synthesize the evidence? Does it start writing me summaries? If so, how does it do that? Does it do it reliably? And critically, how can I know? So ChatGPT, our old friends, are mindfulness-based interventions effective for smoking cessation. ChatGPT thinks they've shown some promise. However, we don't know how or why. We know that it doesn't enable us to draw on the sum of current knowledge. Yeah, and thank you. Is that the ChatGPT? So that'll be the sort of like the newest paid for ChatGPT, which has been trained on data up to this April. So okay. The problem with these models, of course, is that there's still a time lag between now and then in terms of when they were trained. They can't be trained until they're totally up to date. I take your point that it's more up to date than it was, but it probably doesn't contain paywall documents as well. So I think that that critique stands. Does it enable me to distinguish between reliable and unreliable research? Well, who knows? We don't know what ChatGPT has been trained upon, but we do know that it doesn't try and distinguish in its answers here between, for example, randomized trials, meta-analyses, all that kind of thing. Horoscopes, I think ChatGPT does a great job writing horoscopes. So if you need a horoscope written, I think that kind of situation, ChatGPT is very handy. Connected papers is a nice application for experimentation because it's taking advantage of one of those key enablers I mentioned before, which is increasingly open access of bibliographic data and citation information. And if you put a search in, it will identify some sort of core papers around your search concept, and then it will give you this network of related papers. So it's a really nice, quick way to get into a subject and to explore papers that are related to what you find. It doesn't totally enable me to draw on the sum of current knowledge, but I didn't give it a red X there because potentially if it had more data in the database, then you might want to turn that into more of a tick. But it does enable me to distinguish between reliable and unreliable research in that it gives me the papers and then I have to do what I like with them. Elicits, I'm sure many of you have tried elicits. It's a really interesting new tool. I've asked it the same question. Promising but mixed is what it says here, and it writes me a little summary. Now, this is quite interesting. Again, I've given it the same type of X in terms of sum of current knowledge because it doesn't contain everything that you might expect in a systematic review search. Does it enable me to distinguish between reliable and unreliable research? Well, it does and it doesn't it? It's a source of finding papers. So from that point of view, I can use elicit to identify characteristics of the studies as are actually reported in the text. But what the summary doesn't do is distinguish between different types of research, reliable and unreliable research. So we see this little summary that it's written here. It treats individual studies in the same way that it treats meta-analyses, doesn't give them more weight or less weight, doesn't take account, of course, of whether or not there are overlaps between the studies and the reviews that it's citing here. It's a synthesis of the text that it finds on it. So it's an interesting computer science problem. It's quite handy sometimes to sort of get a quick snapshot of what the papers may be saying, but it doesn't distinguish fundamentally between reliable and unreliable research. So I wouldn't want to use this for anything other than sort of curiosity. I'll put the Cochrane review here, of course, because looking at that, so long as it's up to date, it does enable me to draw on the sum of current knowledge, and it does distinguish between unreliable and reliable research, but obviously takes longer to produce than a quick search. So what I thought I would pretty much start to sort of wrap up with at this point is around some of the sort of like the generative parts of language models using the question answering capabilities of them. Some of the work that I did ages ago now, it seems, on using language models for screening, for example. One of the nice things that in theory you can do with a language model is something called zero-shot learning, which is basically you can use it to make predictions without actually having to supply training data. So it's like a classification, but without all of the pain of having to label up thousands of records, for example, like we did with other classifiers. And what I found here was that you sort of devise various prompts to ask, in this case I was using APIs again, whether or not a particular study was relevant or irrelevant for a given review. And I deliberately tried quite a tough review here on debunking vaccine-related misinformation. And I also chose one which we published after the data were used for training ChatGPT back then. And that meant, of course, that I wasn't getting contamination between the review saying that these were about this, these studies were about this review or relevant for this review, and the little experiments I was running. And you can see that we get improvements in precision and recall as we go through the generations of different GPT models there. And I didn't really take this much further than this because what I was finding was that it was very difficult to devise a prompt which reliably gave me all of the true positives, so all of the relevant studies that I wanted, and without pulling in loads and loads of irrelevant records. So you've seen the balance on the longer prompt there, which is probably about as good as I got it. So if you were doing a very rapid piece of work, you might take the fact that it's basically out of what have we got here, 1,200 documents. It was able to screen them down for me down to a very few. So the number of false positives was only 103, but at the loss of 5 relevant papers which we would have missed from the review had we just used that. So the other challenge for this was that I needed to know quite a lot about the review and about the included papers and the performance of the language model on those included papers before I could devise good prompts. And so the challenge here is a mechanism for devising good prompts prospectively before you know what's relevant and irrelevant. And that's work that is no doubt ongoing by various people. This paper just came out recently on medRxiv. where basically what they did was used the language model to predict whether something was a diagnostic test accuracy study or not. So basically a study type classifier, rather than saying, does it belong to this review or that review, a sort of like a higher level classification. And they got very good results for the reviews that they tested that on. The other really interesting area for language models is on data extraction and information extraction. And earlier language models had this something called a context window, which was the sort of like the length of text that you could use, that you could process. Newer models have much larger context windows, so you can essentially process a whole paper or multiple papers at once now with them. So I've experimented here with Claude 2. And you get really interesting results from information extraction from PDFs. So this is the smoking cessation stop advisor trial. If prompted to give me the PICO essentially of the trial, it will extract accurately and succinctly the PICO. Interestingly here, I wanted in tabular form the outcomes of the study. So it both managed to put a nice table together for me, but also, interestingly, identify information partly from the text and partly from a table in order to sort of bring the overall results as well as the subgroup analyses results together. And it then did that as well when I said, give me the secondary outcomes. So some of the rows came from a table and some of the data came from text. What was interesting here is it got it all right. These values were correct. Lastly, for fun, I said, give me the risk of bias as a test by Copper and Rob tool. Didn't even spell it out, just said Rob. And it quite correctly responds saying there's no risk of bias assessment in the paper, but it then obviously knows what a risk of bias assessment looks like using that tool, and then correctly identifies the various different aspects of the study. So there's quite a lot of interesting, promising suggestions that we could use this sort of thing in systematic reviews. What we of course need are scaled up evaluations. It's very easy to do this sort of thing and be quite impressed qualitatively with the results, but obviously we need to scale this up. And one of the challenges there, of course, is that with many of these models, the actual use that you can make of them is relatively limited, even when the paid for stuff. I frequently find that I'm being told by whichever language model it is that it's too busy and I should come back later. So I wanted to touch on this problem of bias, which no doubt you'd have heard about, because the reinforcement learning that I mentioned before and other features around these published models has tried to reduce the apparent bias in models and apparent toxicity that's generated. But it's not 100% successful, and it can't be. So for example, this is a relatively old model now, and I've just got the terms closest to boys and the terms closest to girls on the right there. The terms closest to boy girl, men, young women, etc. What have we got? We got beach, we've got brothers, we've got boy band, friends, loving drummer, etc. The words related to girl are not exactly the same. We've got love, we've got beautiful, we've got women, children, kids, Phillips. We've got school, we've got bad, man, boy, singing, spice, kiss, friends. There is a clear gender difference there in terms of the relatedness of these words. And in ChatGPT, again, you can see in this example here, basically ChatGPT thinks that doctors are male and nurses are female. And this sort of thing is really difficult for the reinforcement learning to change because it's encoded actually within the model in those vectors itself. And so when we're using these tools, we have to be really mindful of the fact that the biases that were present in the training data will be encoded within the language model itself. Tool producers are not doing a huge amount about it, really. They're trying to remove toxicity from the training data to some degree of success. They're trying to filter pre and post responses from the language models. And a favorite tactic you could say at the moment is reporting how toxic models are. So these standardized tests that they run the models through and say, this is how toxic model is, and it's better than their model. And it's almost as though, well, we've done our job now. We've reported how toxic the model is. So there we go. It's over now to the users to decide how to use it. So the models fundamentally are still being deployed with full knowledge that they generate toxic material and are biased. So just to finish off, I just wanted to leave you with a sort of like just a sort of a way of thinking about what's going on in some of these tools. So ChatGPT is just a language model. It's not a database. It doesn't have an external source of data. It's not comprehensive. It's not up to date. It's useful for some things, not answering questions using research evidence. Connected Papers is nice. It uses open access data. It doesn't use a language model, but it's certainly worth exploring. Elicit, EpiReviewer, this sort of like this new concept of having a database with a language model with machine learning in order to identify research, and in Elicit's case to extract information and to summarize research. Could be comprehensive if the data they're based on is comprehensive, but critically the summary tools and the extraction tools need more work. They don't take account of summary study size, for example. The last example I gave you there on information extraction, Claude 2, there's lots of language models that will do this for you. That was just like a convenient one to use for the example. Using these for data extraction looks promising. The challenge is making sure that if information isn't present in the document, especially, that the language model then doesn't just make something up instead. We need to find out more about how to sort of limit these possibilities where the language model starts to make stuff up. So in conclusion, there are many promising new tools out there. Thanks to open access data, more compute resource, and advances in NLP, natural language processing, and machine learning. But it's really important for us to consider those questions of bias, which are definitely alive, and bias is definitely present in these models. We need to get better at critiquing the validity of the tool and the reliability of a tool for a particular use case. In particular, at the moment, we should not be trusting summaries that are based on sort of reading across documents, because we don't know how, it's a relatively new, well, summarization has been around a long time. Using the language models to do it is relatively new, and we know that there are clear problems with doing it. So we can use them as a first pass as something interesting, but we shouldn't rely on them. In terms of whether they're a game changer, looks like they probably are. But the risk, certainly in terms of doing good evidence synthesis, is whether they increase our reliability and our efficiency of doing evidence synthesis, or actually they are sort of almost like they're too seductive, and we start using them and other people start using them. And actually what happens is we end up with increased uncertainty and an increasingly less reliable evidence synthesis. So we've got to be mindful of that. So I hope I've left plenty of time for us to have some sort of questions and discussions. So thank you. I'll have another look at the questions which kept popping up.